everyone. I'm Kim Bremer, your host today for another edition of Bova News, keeping you up to date on the cattle industry's latest in technology, management, genetics, and more. It's a well-known fact that heat stress can present a major challenge to dairy cattle productivity during the hot summer months. Knowing how to proactively manage heat stress, monitor, and intervene when you see signs are all critical to the success of your operation through these challenging seasons. In today's webinar, we'll be speaking with a heat stress expert and a biosystems expert to tell us about the implications heat stress can have on a dairy and ways to alleviate these stresses. Our first presenter today is Geoffrey E. Dahl, who's the Harriet B. Weeks Professor in the Department of Animal Sciences at the University of Florida in Gainesville. He previously served as chair of the department for 12 years, serving as liaison between the university, livestock producers, and allied industries in Florida. Geoff conducts applied and basic research with direct impact on dairy production. Specific research interests include effects of photoperiod manipulation on production and health, the impact of frequent milking and early lactation on milk production, and heat stress abatement during the dry period on cow productivity and health. Those research efforts are disseminated through his extension programming in the U.S. and abroad. Geoff has been invited to present his research findings in 20 countries and also has active extension program efforts in a variety of developing countries, including Sri Lanka, Nepal, Rwanda, and Ethiopia. Geoff has authored over 150 peer-reviewed papers and numerous symposium and popular press articles. He's trained 27 graduate students and postdoctoral fellows. Geoff is a member of several professional and honorary societies, including the American Dairy Science Association, the American Society of Animal Science, the Society for the Study of Reproduction, American Association for the Advancement of Science, and the Endocrine Society. He served as president of ADSA from 2018 to 2019, and Geoff has received numerous awards, including the Award of Honor from ADSA and as a fellow in the American Association for the Advancements of Science. Welcome, Geoff.
Thanks, Kim. Happy to be with you today and talk about the effects of heat stress. Well, today we're going to talk about maximizing cooling resources in targeted areas on the dairy. So when we think about this outline for the presentation, I want to talk just a little bit about effective cooling approaches, because I know Dr. Janni is going to talk much more about that in the second half of our session. We're going to talk a little bit about water use estimates and why we need to think about other ways that we might be able to get animals cooled off as we move forward. And then we'll get into the meat of this discussion, talking about priorities of cooling. Is it lactating cows, dry cows, or calves? And finally, a couple of thoughts to summarize. So in terms of effective cooling, this is really the heart of what we need to do. We have found in our high humidity, high temperature environment here in Florida that really the only way we can cool cows is with a combination of fans and soakers. We need to get those animals soaked to the skin and then get them cooled off by having evaporative processes move that water and heat off of their bodies in order to effectively get them cooled in our high humidity environment. And here are some data that bear this out from Kansas State University, where they showed that animals that were subjected to a combination of soaking at higher intervals, so every 5 minutes, and fans, that actually produced the most effective cooling of those animals. One of the issues, though, is that we're using a lot of water that goes to waste. We did a quick summary of occupancy or use of our soakers and fans in this arrangement and found that at about 25% of the time, animals were in front of those soakers when it came on at 5-minute intervals. But when animals were not there, obviously that water was going to waste. So we've actually started, and there are some of these on the that are available on the market already, to look at some smart soaker systems that actually will only activate when an animal is at the feed line and in front of the soaker to more effectively use the water that we have available. So we know that heat stress during lactation is going to reduce productivity of cows, but one thing that we don't always think about is when in lactation that heat stress is going to have the greatest impact. These are some data for some early lactation cows that we subjected to heat stress. So the solid triangles are the animals that are in our cooling group, and the open circles are the animals we subjected to heat stress. And you can see that when we started, obviously none of the animals were heat stressed, but then as we started in the first couple of weeks to heat stress those animals, there was a reduction in milk output of the cows that were in our heat stress group, not surprisingly. But as we ended the study in that week 8 and 9 section, you can see that the animals that had previously been heat stressed, when we applied cooling to them again, they kind of came back to the same level of productivity as the animals that had been cooled the whole time. So that suggests that animals can recover from a heat stress event, although it does seem to affect or it appears to be affected by where those animals are at in the lactation cycle. Because when we did the same sort of study in mid lactation, late lactation animals, we saw that there was a significant reduction in milk output of the animals that were heat stressed in the open symbols relative to those animals that were cooled. Yet when we stopped the heat stress towards the end of this study in week 11 and 12, you see that those cows that had been heat stressed didn't come back to the same level of productivity as the animals that were cooled the whole time. So that suggests that perhaps different from what we might perceive as to be the effect, cows that are in mid and late lactation actually may suffer longer term consequences of heat stress events versus those animals in early lactation. So it's something to think about when we think about which group of animals we actually want to get cooled during lactation if our resources are limited. So we know that heat stress during lactation is going to drop dry matter intake. It reduces yield, as I've just shown you some data to support that. And there are other effects of this as well. There are animals that are heat stressed in lactation have to get rid of that heat, and that requires additional movement of energy towards those processes and takes them away from productive processes such as milk production. And that recovery, as I've just shown you, is going to be dependent on where those animals are at in lactation, how long that heat stress might last, and a number of other factors. But our question and what we've been working on for the last 15 years or so is what happens when we heat stress dry cows? Obviously, those animals aren't producing any milk, but are there impacts of heat stress during the dry period that might persist in that next lactation? So I'm just going to cover a little bit of what we've done. We're going to focus in the first part of the presentation on impacts on the cow, particularly on milk yield, although we'll cover a little bit on these other influences as well. And then we'll shift over and look at the impacts of heat stress on that developing calf, because there are some short-term and long-term impacts of heat stress on that developing calf, none of which, as you might imagine, are going to be positive. So just to set the stage, I wanted to show you the barn that we do this in. Most of our work is conducted at the University Research Center. This is our barn. It's a sand-bedded 4-row freestall barn. We've got fans over the beds, and then we've got soakers along this feed line here. So very typical of what we would see in terms of housing in the Southeast, and actually very typical of housing that we'd see around the country, with the exception of we don't have any curtains or sidewalls on this barn. But I think that gives you some idea of the relevance and the application of what we do to the more general industry standards. Our fans come on at 70 degrees, and the soakers are on for a minute every 5 minutes when we hit 72 degrees. So both of those are controlled by thermostats. And we're going to have those operational year round here in our environment. So if we simply turn off the fans and soakers, we induce heat stress in our animals. So what we do is have the cows starting when they're dried off, they're put onto our heat stress or cooling treatment. They're going to remain on that treatment for their entire dry period. And usually in most of our studies, we've had those animals on a 6 to 7 week dry period. So about 45-day dry period. And we see that when we just limit access to fans and soakers, so when the animals are in this shaded barn but don't have access to the fans and soakers, they have an increase in rectal temperature. These are data from one of our studies, shows that there's an elevation in the morning, becomes significant in the afternoon, and we're typically looking at about a 0.4 of a degree, so about a degree Fahrenheit increase in rectal temperature in the animals that are in our heat stress treatment versus those animals that are in our cooled treatment. And again, that's for the entire dry period. And what that does is causes a reduction in milk output in the next lactation. So what I've shown here are the production results from one of our studies. The solid symbols are the cows that experienced cooling when they were dry, and we compared them to the open symbols, which are the cows that were heat stressed when they were dry. It's important to point out that there are no differences in how we manage these cows after they calved in. They were all calving at about the same time. They were managed as a group in the same pen, milked at the same time, fed the same diet. The only difference between these two groups of animals was what happened back here in the dry period when the animals were either heat stressed or cooled. So those are data from one study, but we and others have actually completed a number of studies that all show the same type of thing. And I've summarized those in this figure. The solid bars are the animals that are cooled when they're dry, and we compare them to the open bars, which are the animals that were heat stressed. And in every case, you can see that there's a reduction in milk yield in that next lactation when animals are heat stressed when they're dry versus the animals that are cooled. So one of the factors that is significantly influenced by dry period heat stress is memory development. So we see here data from cows that were either heat stressed or cooled. When we looked at alveolar number, which are the sort of secretory units of the or combination of secretory cells that produce milk in the mammary gland, and we see that that alveoli number is going to be linked to capacity for milk production. And the animals that were heat stressed actually have poorer mammary development and growth during that dry period. And that accounts for that persistent effect on milk yield in that next lactation. We've also looked at this and other aspects of it in a commercial setting. So here are data from a study that we did looking at animals that were dry during the hottest months of the summer here in Florida and comparing those to animals that were dry during the coolest months of the year. We can see that cows that were dry in June, July, and August, they were housed essentially on pasture with no shade. And we compared it to cows that were dry in December, January, and February on the same farm with high level of management and very consistent feeding and other management aspects. Cows that were dry in the summer produced less milk in that next lactation relative to the animals that were dry in the cooler months of the year. They also experienced increased rates of mastitis, of respiratory disease, and of retained membranes when we compared them to the animals that were dry during the cooler months of the year. So supporting the data that I showed you with animals that were heat stressed during the dry period, producing less milk in that next lactation, they also had a greater tendency to have increased incidence of disease in that next lactation as well. Another aspect that's negatively impacted by dry period heat stress is their subsequent reproductive performance. So same study where we had those animals dry in the hotter months of the year and compared them to a genetically similar group of animals that was dry during the cooler months of the year. And we see that the number of breedings to get those animals pregnant was increased. Their days in milk to actually becoming pregnant was increased as well when they were dry during the hottest months of the year versus those animals that were dry during the cooler months of the year. And just to emphasize, the animals that were dry during the coolest months of the year would have been trying to get bred during the hotter months of the year. So any acute effects of heat stress would have dampened this response a bit. They were also at a higher level of production. So both of those factors would tend to limit reproductive performance, yet they were still improved relative to the animals that were dry during the hotter months of the year. So a longer term effect on production, on health, and reproduction in that next lactation when cows are heat stressed during the dry period. Another aspect we've looked at is animals that are coming into their first lactation, so first calf heifers. When we cooled them for the final 60 days of gestation, we saw a similar impact as to what we observed in the mature cows. So here we have in the blue line the animals that were cooled for the last 8 weeks of pregnancy compared with the animals that were heat stressed. And we see that in that first lactation, the animals that are cooled produce more milk versus the animals that were heat stressed during late gestation. So very similar to what we observe with mature cows. So when we look at the effects of heat stress during the dry period on the cow herself, There are profound effects on milk yield for that next lactation. We've seen impacts on metabolism in the animals, particularly during the dry period, more so than after the animals calve in. There are impacts on immune function, which probably leads to some of those effects on disease incidence in the animals that are heat stressed when they're dry versus the animals that are cooled. And we think this is all coming back to dysfunction of placental activity in the animals that experience heat stress during the dry period versus the animals that were cooled. And that can obviously then have an impact not only on the cow, but also on that developing fetus. And so now I want to shift gears a bit and just talk about impacts of late gestation heat stress early in life on those calves and ultimately on their performance and what they might pass on to their offspring as well. So one of the impacts of heat stress during late gestation is that cows will tend to calve in earlier, and that's going to reduce calf birth weight. But that's only part of the explanation for that reduction in birth weight that we see. These heat stress calves actually are going to experience a challenge from placental function and the efficiency and nutrient transport and gas exchange. So they tend to be smaller, not only because they spend less time in utero, 4 or 5 days during gestation, but also because of that placental dysfunction. So we've seen repeated incidents of lower birth weight in animals that are heat stressed during late gestation versus those that were cooled. And we looked at how long this extends out. Weaning weight is still reduced in the animals that experienced heat stress during late gestation versus those that were born to cooled dams. And even though all the animals are managed identically once they're born, those animals still tend to have a lower weaning weight versus the animals that were cooled. One of the other negative outcomes of late gestation heat stress is immune status. So here we have the total immunoglobulin concentration in serum of calves that were in the open symbols heat stressed in utero versus the animals in the solid squares that were cooled in utero. And what we find is that from the first day of life, there is less circulating immunoglobulin in the animals that were heat stressed in utero versus those animals that were cooled. And that extends out through that first month of life. So this indicates that there is poorer absorption of immunoglobulin from the animals that were heat stressed in utero versus the animals that were cooled. So less uptake of immunoglobulin in those calves that experience heat stress in utero. And we think that that's probably due to acceleration of gut closure in those calves that experience heat stress in utero versus the animals that are cooled in utero. So here we see that the gut closure is accelerated, so higher turnover of cells within that intestinal lining of the calves that were heat stressed in utero versus the animals that were cooled in utero. And that means that we probably can't manage our way out of this once the calf is born because the process is already underway. And that explains why those animals are challenged from an immune status standpoint through that first month of life and have lower immunoglobulin uptake. So we were interested in looking at some longer term effects of in utero heat stress on these calves. And in order to do that, we took records from calves that were born to across a number of our studies for about a 5-year period. So we have very consistent management of our calves at the university facility. So we were comfortable in putting together records of calves across multiple years. And all of these indicators did the same thing across the years. It was really just to get to a point where we had enough numbers of animals to look at some of these statistically. So we ended up with about 75 calves from our cooling and from our heat stress groups across this 5-year span. And we looked at both bulls and heifers, but most of our emphasis was on the effects on the heifers, both early in life and then as those animals matured and entered the productive strength. So birth weight differences in the combined data set just showed the same thing that we observed in the individual studies, with animals from cooled dams actually having higher birth weight than animals from heat stress dams. We also found that that difference persisted at weaning, with the calves from heat stress dams having a lower weaning weight versus the animals that were from cooled dams, and even to a year of age, around the time of puberty, that difference in body weight persisted. So the calves that a year earlier were born to a heat stress dam actually had lower body weight at this point versus the animals that were born to a cool dam. So long-term effects on growth in those animals. And we've looked at this in some other ways, and it suggests that there's a difference in the overall pattern of development in these calves that were born to heat stress dams with a greater propensity to accumulate fat versus lean growth. We've also looked at survival. And the line to focus in on here is the heifers that left the herd before puberty. Most of this was due to sickness. And we see that the calves that are born to the animals that were heat stressed have greater propensity to leave the herd versus the animals that were born to cool dams. And that, of course, leads to fewer of those heifers than making it through their first lactation when they were heat stressed in utero versus the animals that were cooled. Reproductive performance is also diminished in the calves that are heat stressed in utero versus the animals that are cooled. So here, just in this first study, very low numbers, but all showing the same trends, that the calves that are heat stressed would have no difference in age at first AI, but more services to get them pregnant. And they ended up having greater age at pregnancy overall versus the animals that were born to cooled dams. And then we looked at productivity in the first lactation. So just to set this up, it's milk production in the first lactation of heifers that 2 years earlier in the open symbols had either been heat stressed during their final phase of gestation, or they were cooled in the solid symbols. So these two groups of animals for 2 years had been managed identically from the time they were born till the time they calved in, and even through this first lactation. The only difference in treatment of these animals was that during the final phase of gestation, the animals in the open symbols experienced heat stress, and the animals in the solid symbols were cooled. So a significant reduction in milk yield in that first lactation, on the order of about 8 pounds a day on average in the calves that had been heat stressed in utero versus those animals that were cooled. Now, there were no differences in genetic potential between these two groups of animals, but we thought that perhaps those impacts on growth could explain some of this. And then maybe the animals that were heat stressed in utero would actually have greater growth during that first lactation and be able to recover as they moved into the second lactation and beyond. When we looked at body weight, though, it suggested that there was no difference in growth between these animals during the first lactation. So here are the weights right after the animals calved in, and there's no difference, and there was no difference in body weight throughout that first lactation. So it suggests that that compensatory gain or increase in body weight had already occurred during year 1 to 2 of life. So the heifers were all of the same weight at the time of calving, so they weren't going to catch up in that second lactation or beyond. And in fact, when we've gone on with greater numbers of animals, because we've continued to sort of accumulate data on this, we see that that effect of in utero heat stress persists. Here's the difference in the first lactation in panel A. We see in the second lactation the same response, lower production in the animals that were heat stressed in utero versus the animals that were cooled in the second lactation, and even into the third lactation. So long-term negative impacts of in utero heat stress on lifetime yield in these calves versus their herd mates that were experiencing cooling during that late gestation period. In addition to that, we see that survival is reduced in the animals that were heat stressed in utero. You can see that in panel A, the cool daughters are the animals that experience cooling late in gestation, and they had greater survival and persistence in the herd versus the animals in the orange line that were heat stressed in utero. And it turns out that it's about a year less time time that calves that experience heat stress in utero are going to spend in the herd versus the animals that were cooled. Perhaps one of the bigger problems, though, is that they pass that lower survival on to their offspring. So here are the granddaughters of those original calves. Even though there was no difference in how these animals were managed throughout their life, they tended to leave the herd at a faster rate than the animals that were born to cooled animals. So that's suggestive of an epigenetic or a fetal programming impact of late gestation heat stress, such that the calves that experience that heat stress are going to be less productive and pass on that poorer productivity and survival in the herd to their offspring as well. So in summary, heat stress late in gestation is going to be a negative for that dam in terms of her yield in the next lactation. She's also going to experience some reductions in intake and mammary growth. And we think this is related to placental dysfunction, which then also impacts her daughter. And so postnatally, that heifer that's born to that cow that's heat stressed is going to have a lower birth weight. She's going to have a lower survival rate. And when she moves into her first lactation and beyond, she's going to be less productive than the animals that experience cooling during that late gestation phase. And this is kind of a hallmark of fetal programming. And we see that there are other impacts that we really can't reverse once that calf has been born. So we can't manage our way out of this once the animals are born. We have to manage them effectively during late gestation, both for the impacts on the dam, but also the impacts on the heifer. So with that, I will turn it over to Kevin to talk about how we actually get cows cooled off.
Thank you, Jeff. Our second presenter today is Kevin Janni, a professor and extension engineer working part-time in the Department of Bioproducts and Biosystems Engineering at the University of Minnesota. Kevin earned his Bachelor of Agricultural Engineering degree at the University of Minnesota in 1976 and graduate degrees at Purdue University in 1977 and 1979. He joined the University of Minnesota faculty in 1980. He currently teaches an air quality and pollution control engineering course and helps teach both the process control and instrumentation course and the capstone design course. He works closely with both the dairy and poultry extension teams. He's authored or co-authored over 65 research publications and over 85 conference or professional meeting papers related to ventilation, air quality, odors, and biofilters associated with animal agriculture. He produced 6 videos on animal feeding operation odors and their mitigation, has written numerous extension articles, and made presentations related to ventilation, air quality, heat stress, biofilters, and biosecurity. He was awarded the American Society of Agricultural and Biological Engineers Henry Giese Structures and Environment Award. He's an ASABE fellow and a registered professional engineer in Minnesota. Currently, he has 2 papers on modeling heat exchange between a lactating cow and her surrounding environment in review to be published. He's also collaborating with research teams dealing with biosecurity for poultry and swine facilities and the development of a national manure database. Welcome, Kevin.
It is a pleasure to be here today for this webinar on heat stress and cow cooling practices. You've just heard Dr. Dahl describe numerous negative consequences and impacts of heat stress on lactating cows, dry cows, and heifers. My task is to talk about some of the things that you can do to help your cows manage heat stress during hot weather. Today, I will outline several common cow cooling practices and tools, and then I'll mention 2 other practices that a few researchers are thinking about. When talking about cow cooling, I like to think in terms of having the right tools for the job and knowing how to use those tools to get the job done right. Let me note that the level, duration, and type of heat stress your cows experience depends on your climate. In general terms, the southeastern US has hot and humid weather for several months. In the southwestern part of the US, the weather is hot and dry for several months. In the upper Midwest, we typically have heat stress for shorter periods of time, but it can be impactful. Unfortunately, heat stress levels and duration are increasing as dew point temperatures rise and nighttime temperatures rise. We are seeing more and more heat stress for our high-producing cows. These weather conditions impact the amount and type of heat mitigation you might choose to install and use. But before I talk about cooling practices, I want to provide some background about how cows exchange heat with their surroundings and the environment. First, we need to remember that cows generate metabolic heat, That is heat generated during digestion, milk production, growth, and locomotion. Highly productive cows produce more heat than low-producing cows. High-producing cows can produce over 3,800 BTUs of heat per hour. For cows to maintain their body temperatures within acceptable ranges around 101 degrees Fahrenheit, they need to balance the metabolic heat produced and heat gained from sunshine with their heat losses to the environment. Cows exchange heat with the surrounding environments by respiration, water evaporation, convection, and they pick up heat from sunshine. Respiration heat loss depends on both respiration rate in breaths per minute and the volume of air per breath. Cows can increase their respiration rates up to a point, and they can either breathe deeply or shallowly. Cows get rid of heat through respiration by warming up the air they breathe in if the ambient temperature isn't too high, and they lose heat via evaporation. They also lose heat by evaporation in the respiratory tract. Evaporation of water from the cow's skin is another way of cows get rid of body heat. It is important to know that it takes energy to convert the liquid water to water vapor. So evaporation can be used to get rid of body heat through respiration and evaporating sweat. Sweat is the moisture that comes through the cow's skin. Cow body heat is used to evaporate the sweat. For cows that are able to sweat and stay hydrated, they need access to plenty of clean water. We also use evaporation to help cows cool by wetting a cow's skin with water with sprinklers. For sprinklers to work, cows need to use body heat to evaporate the water. The third way cows get rid of heat is by convection. Convection is when heat is transferred to moving air past the cow. Cows lose heat to the air if the air temperature is below the cow's skin temperature. Convection can be increased by keeping the air temperature lower and increasing the air temperature past the cow. Cows lose more heat if the air velocity past the cow is higher and the surface area exposed is larger. Cows often stand more in hot weather, which exposes more skin to air, increasing convective heat loss. Another important method of heat exchange is radiant heat. Today, I'm going to limit my discussion to the heat gained from the sun. Sunshine warms cows. Radiant solar energy can add over 3,000 BTUs per hour to a cow's heat load at solar noon if she is in the sunshine. Remember that a high-producing cow generates over 3,800 BTUs per hour of metabolic heat. If she's in the sun, her heat load nearly doubles. There is another method of heat transfer called conduction. This is heat exchange between surfaces in contact with each other. But standing cows have little contact with any other surface for conductive heat loss. So as I talk about cow cooling practices, keep in mind the methods of heat exchange and the factors that impact that heat exchange. Here is a list of common cow cooling methods. I will go through each separately. You may recognize an equipment supplier or a manufacturer in some of my pictures. That is not an endorsement. The equipment is being shown to illustrate a point of our education. I'm not endorsing the equipment shown. A common and important practice to reduce heat stress is to provide cows and heifers shade. Obviously, cows housed in barns or who have access to a barn or a shed with a roof will have shade. Shade reduces the amount of shortwave radiation and heat from the sunshine that a cow absorbs. Shades don't block all of the radiant heat because shade roofs can heat up and transmit some radiant heat, but a shade reduces that radiant heat load a lot. A shade can eliminate most of the 3,000 BTUs per hour of solar heat gain a cow can absorb at solar noon. Again, cows in barns have shade, but many cows and heifers on pasture or in open lots may not have shade. Shade can be provided by movable shade structures. Some beef producers use movable shades like the one shown in the picture in the lower left side of the slide. These shades usually use shade cloth that is stretched over a frame. Researchers at the University of Minnesota West Central Research and Outreach Center use photovoltaic solar collectors to provide shade to cows in grazing paddocks. It is recommended to provide 40 square feet per cow to avoid crowding under the shade. Another practice to help cows in hot weather is to increase the ventilating rate through the barn. In hot weather, barn ventilating rates are increased to their maximum. One goal of the air exchange is to prevent the barn temperature rise from exceeding 3 degrees Fahrenheit. Cows in the barn generate heat, which heats up the barn. To avoid raising barn temperatures more than 3 degrees Fahrenheit, you need to move around 825 cubic feet of air per minute per cow or more. There are numerous ventilating systems used to ventilate dairy barns. Two broad categories are natural ventilation and mechanical ventilation. Within the mechanical ventilation system category, there are different systems, including cross ventilation, tunnel ventilation, and push-pull or neutral pressure systems. When I talk about ventilating systems, I'm talking about air exchange between inside the barn and outside the barn. Mixing fans used in the barn to increase the airspeed within the barn are part of the cooling system, but not the ventilating system in this presentation. Let's take a look at natural ventilation first. In hot weather, the main driving force for natural ventilation air exchange between inside and outside is the wind. The buoyancy effect of warm air rising and moist air rising helps, but it is not as important in hot weather as wind. To maximize natural ventilation in hot weather, you want your sidewalls and end walls to be as open as possible. You might want as much building height as economically possible, too, to catch as much wind as possible. Over the past 20 to 30 years, we've seen sidewall height recommendations increase from about 10 to 12 feet up to 14 to 16 feet or more. You also need to avoid making the barn excessively wide when relying on wind. Most barns are less than about 110 feet wide. Locate your barn on a rise or high spot. A retired extension engineer at the University of Wisconsin used to say, "Build on a knoll, not in a hole." In most areas, people want their barns oriented east to west to catch southerly breezes to get as much air exchange as possible in hot weather. Local conditions may suggest other orientations. And finally, you want to minimize obstructions around the barn that can block the wind. Trees, other buildings, the milking center, and equipment can block the wind and reduce air exchange. Many years ago, I visited a barn that was using a very thick bird netting, which reduced their natural ventilation. Unfortunately, it is common to have calm winds during hot weather. So there are times when naturally ventilated barns have limited air exchange. These naturally ventilated barns have mixing fans to provide air movement at cow level to help cows get rid of body heat. I'll talk about mixing fans more later, but remember, mixing fans are not really providing air exchange through the barn to avoid increasing that barn temperature too much. Let's move on to mechanical ventilated barns. Mechanically ventilated dairy barns use fans to either blow air out of the building, into the building, or both into and out of the barn. For this presentation, when I talk about fans that ventilate a barn, I'm talking about fans in the walls, and I will focus on hot weather ventilation. Cross-ventilated dairy barns bring fresh air in one side of the barn and blow it out the other side. Most cross-ventilated barns have 4 baffles that force the air down towards cow level at each baffle. In most cases, these barns have ventilating rates based on providing an air velocity under the baffle of about 6 miles per hour or 528 feet per minute. Air moving at that velocity below the baffles will generally provide sufficient air exchange to keep the barn temperature rise in the range of 1 to 2 degrees Fahrenheit. This means that the warm air entering the barn increases by 1 to 2 degrees Fahrenheit by the time it leaves through the exhaust fans. This slide shows a sketch and pictures of a 10-row barn with 4 baffles. Tunnel ventilated barns are another type of hot weather mechanical ventilating system. Here are pictures of the fan or exhaust end of 2 tunnel ventilated barns. Tunnel ventilated dairy barns bring in air in one end of the barn and blow it out the other. The barn acts as a tunnel. Stall barns can be tunnel ventilated in the summer. The ventilating rate for tunnel ventilated barns is based on the cross-sectional area of the barn and using a velocity between 3 to 6 miles per hour or 264 to 528 feet per minute. The temperature rise in the tunnel ventilated barn depends on the barn length, the number of cows, and the ventilating rate. In most cases, well-designed tunnel ventilated barns have barn temperature rises of less than 3 degrees Fahrenheit. So if the outside air enters at 95 degrees Fahrenheit, the air temperature leaving the barn will be up to 98 degrees Fahrenheit. It is very important not to restrict the inlet area or have openings near the exhaust fans. If the barn has a gable roof and no ceiling, the air flowing above the cows provides little value, so some farms add baffles or mixing fans to push air closer to cow level. A few years ago, I saw a barn in Nebraska that some call a neutral pressure or push-pull ventilating system. On one end of the barn and in some sides, there were fans blowing air into the barn. At the other end of the barn, there were fans blowing out of the barn. The barn also had mixing fans with misters to increase air velocity within the barn and provide cooling. I'll talk about cooling with misters in a few minutes. Another way to help cows get rid of heat is to increase air velocity past the cows. Mixing fans create drafts to help cool the animals and break up stale air spots. Some people use high volume, low speed fans. These fans break up stale air, but they do not create much of a draft for cooling. Most people use axial fans that create a higher air velocity for about 30 to 40 feet downwind of the fans. It is important to point the fans downward so that cows feel the airflow from the fans to increase their convective heat loss. Mixing fans can be located over feed alleys where the cows stand to eat and over the free stalls. In all cases, you want to point the fans downward so that cows feel the airflow or fan throw. The guideline for installing a row of mixing fans is to place the fan every 10 times the fan diameter in feet. So if you're using 3-foot diameter fans, a fan should be located roughly every 30 feet. If you're using 4-foot diameter fans, they should be located at roughly every 40 feet. These are rough guidelines. Let's move on to another category of cooling tools based on evaporating water and either cooling the cow or cooling the air. Remember, evaporation takes energy to convert liquid water into water vapor. One option is to soak a cow's back so that her body heat can be used to evaporate the water and help her get rid of her body heat. Another option is to spray small droplets of water into the air with a mister, where heat in the air evaporates the water droplets, converting the liquid to a vapor which cools the air, lowering the dry bulb temperature. The picture in the upper right corner has a small white spray nozzle that emits a mist when cooling is needed and the fan is running. Picture in the lower right has misters running with a mixing fan. Picture in the lower left is a low pressure feed line water sprinkling system with nozzles. You might be able to see the water spray, which has a whitish gray color. Feed bunk sprinkler systems are fairly common. They work well with mixing fans. A combination of evaporative cooling and a draft can be very effective in dry climates. There are two key things with sprinkler systems. One is to make sure that the sprinklers are turned on and off. It is important to give the water time to evaporate from the cow's back. It is common to use timers to do this, provide the sprinkler on for a time or off for a time. One guideline is to use sprinklers for on for 3 minutes and off for 12 minutes to let the cows dry off. The amount of time off can be reduced as temperatures increase, but it is important for the wet coat to dry out before being wetted again. Second, don't overspray. Avoid spraying so much water that the water drips off the cows or gets the udder wet. You also don't want the spray to get onto the free stalls because the nozzles are pointed too high or sprayed too far. You want to keep the free stalls dry, and you don't want the spray to wet the feed in the manger area. One of the challenges, as Jeff noted in his presentation, is systems when the systems run the bunk sprinklers, even though the cows aren't there. I've heard about the new systems, which Jeff was talking about, where there's detectors that indicate whether cows are present or not. These cow detectors can reduce water usage. The detector might control 2 nozzles. No cows, no spray. Finally, excess spray can add water to the manure system, which is going to be a problem. Here are pictures of mixing fans with misters. It is important that the water droplets be very small so that the water droplets evaporate before they reach either the freestall bed or a feed manger. It is also important that droplets be introduced near the ventilation inlets so that the droplets evaporate and cool the barn air before the air is exhausted from the barn. Clean water is important because the misting nozzles can become plugged with dirt. One area where cow cooling is commonly needed is in the holding area. Here is a picture of a naturally ventilated holding area. You can see the open ridge. There are several mixing fans pointed downward, and there's a sprinkler system in the exit lane to soak the cows as they leave after being milked. Cow body temperatures can rise substantially while the cows are crowded together in the holding area for up to an hour. There are a few other cow cooling ideas that have been studied but are not commonly used. I just want to take a moment to mention two. One is air conditioning. When I started working with dairy producers in the mid-90s, I heard about 3 farms with stall barns that were using air conditioning to cool the barn. 2 farms that I talked to about their air conditioning systems were using them to maintain milk production of their very high producing cows. I am aware of one engineer that has done some analysis to assess whether air conditioning could be cost effective. A few years ago, I had a team of engineering students investigate providing cooling using a geothermal system, heat pumps, and solar energy. More analysis and deep pockets are going to be needed. Finally, another idea that has been researched is using cooled water mattresses. The idea is to enhance conductive heat loss from the cows lying on a cooled mattress in a stall. One challenge to the systems is the problem with condensation on the cooled mattresses when humidity levels are very high. Who knows if either of these ideas or others will be developed and adopted widely. One last point, it is critical that you provide plenty of clean drinking water. Cows need water for digestion, milk production, respiration, and sweating. Cows generate a lot of heat. They exchange heat with their environment by respiration, water evaporation, convection to the air, and they can gain heat from sunshine. Cows and heifers need to get rid of that heat to maintain their body temperatures around 101 degrees Fahrenheit. You can help by providing shade, plenty of ventilation air exchange, increased air velocity past the cows, some evaporative cooling help, and plenty of clean drinking water. With that being said, I turn it back to you, Kim.
Excellent. Thank you, Kevin. A lot of great information presented today. I just have a few questions for the two of you. I'll start off with you, Jeff. What do you think is the most effective way to monitor for heat stress?
Well, one of the things that we've done is try and get away from as much cow handling as we can and use non-invasive methods. So we use respiration rate as a good indicator of where animals are at from a heat stress perspective. And if we see cows, sort of sentinel cows in a pen that are averaging over 60 breaths per minute, that's indicating that we're starting to see heat stress, and that just increases as cows get more and more heat stressed.
And when it comes to profit loss, I know you walked through all the different ways that heat stress affects cattle. Is there any specific place that it affects dairies the most severely?
Well, you're going to get a biased answer from me on this one, but I think that that dry period is one that we don't tend to think about, and it can have dramatic effects, just about probably the same or even more than during lactation, because those effects persist throughout the entire lactation. So if animals are heat stressed, then they're going to produce less milk for that whole next lactation. And then if we account for the impacts on the calf as well, then it really starts to add up.
And is there a way that dairy producers can best prepare for the days they know heat stress will be inevitable?
I would say that they need to talk to someone like Kevin and get a good heat abatement system put into their barns and not think about it a week or two before heat stress starts. They need to have a system installed before the heat stress is going to be there.
And do you think genetics can play a part in heat stress management for those that live in hot weather the majority of the time?
Yeah, there are, and we've actually developed one line here, slick cattle, which tend to have more a better response to heat stress events. They don't go down as much in terms of productivity. They're an animal that has a better thermal regulatory system for hot weather. So that and some other selection overall for animals that are more amenable to hot environments is probably where we're headed in the future.
And Kevin, what do you think is the easiest fix or change a producer can make to their farm today to alleviate heat stress in those hot summer days? What's the most common thing that you take calls about or you get to see? when you visit dairies?
Well, I think the recommendation always depends upon the kind of barn that the person has. So if they have a stall barn, one of the things to do is modify the barn so that they can implement tunnel ventilation. So they can move more air during that hot period and things like that. With naturally ventilated barns, again, it's open up those side walls, open up those end walls as much as you can. Remove any obstructions you have around there. If you've got some lean-tos or some other buildings nearby, trees and things like this. Then you start adding mixing fans, and then you start adding some evaporative cooling kinds of things. If you already have a tunnel ventilated barn and a cross ventilated barn, it's maintain the fans, make sure that they're running properly, full system, full capacity. And then the other thing to watch with those is make sure you're not restricting the inlet or providing a short circuiting an inlet too close to the exhaust fans. And then again, I'm going to come back and say make sure they provide plenty of waterers and things like that. So our guidelines are like 2 feet of water per 20 cows, and then add 25%. Make sure you got extra capacity during the hot weather. Bump it up even more.
Well, and certainly we look forward to keeping up with the research as it continues to evolve, especially in your respective fields. We appreciate all you do to help improve our industry. My thanks to you, Jeff and Kevin, for joining us today and sharing your invaluable expertise and experience. Don't forget to subscribe to the Bova News channel on YouTube, find our Bova News podcast on your favorite listening platform, or find more information at bovanews.com. Thanks for tuning in with us today, and we'll see you next time on another edition of Bova News.